Every time we observe the world, we are bombarded with raw data. A single study might generate hundreds of individual numbers, measurements, or categories. But without a framework, this raw observation is nothing more than static. Take a look at these three distinct sets of observations. We have the test scores of 10 students, the weights of 64-month-old babies, and a list of 300 car sales broken down by brand. Looking at these examples exactly as they appear on the page, the structural patterns are invisible. Staring at a list of numbers or a ledger of car brands tells us almost nothing about the behavior of the group as a whole. Mathematicians do not rely on intuition to make sense of this. Instead, they apply a strict architectural framework to build a complete mathematical profile out of the noise. The very first step is defining the boundaries of what we are analyzing. The total group we are studying is called the statistical population, or populace statistique. The individual components making up that group, a single baby or a single car, are the statistical units, or unités statistiques. This table maps these foundational definitions across our examples. The most critical concept is the caractère, the specific variable measured. Its mathematical nature dictates the entire study's logic, determining every single rule and formula we use moving forward. Data that takes specific, isolated numerical values, like a test score of exactly 60 or 70, is discrete quantitative data. Data representing measurements that fall into continuous intervals, like baby weights grouping anywhere between 5 and 5.5 kilograms, is continuous quantitative data. Contrast both of those with data that expresses non-numeric properties, like the brand of a car. That is qualitative data. Categorizing your data accurately is the mandatory first step. If you misidentify a continuous measurement as a qualitative category, every subsequent calculation and chart you attempt to build will be mathematically invalid. Before we can run advanced metrics, we have to compress these raw occurrences into a structured table. We start by simply counting how many times each specific value appears. This base count is the effective. Look at the definitions here. Summing specific effectives gives the total population, n. We convert raw counts to frequencies by dividing the effective by n. We push further, calculating cumulative frequencies. A running total lets statisticians instantly know what percentage scored below a specific mark. Once completed, this structured table replaces the raw data lists entirely. It becomes the clean, organizing engine block required for all the complex formulas that follow. With the data organized, our first major analytical goal is establishing the mathematical center, or the center of gravity for the entire population. This is the arithmetic mean. We multiply every distinct value by its frequency, then sum them. For continuous data, we use the midpoint of each interval, c. Contrast this with the median, the exact middle point, splitting the total population perfectly in half. Think of the mean as balancing the weight of the values on a seesaw, pulling the center toward heavy outliers. The median ignores the weight and simply cuts the number of points into two equal halves. These parameters successfully locate the center point. However, they leave a blind spot. Knowing the center tells us absolutely nothing about how tightly or loosely the data is packed around that point. Two completely different data sets can share the exact same average. Relying purely on the mean alone is dangerous if it isn't paired with a precise measure of volatility. One group could have all its members tightly clustered around the center. Another group could share that same center line but have members wildly scattered in both directions. To quantify this spread, we measure the distance of individual data points from the center mean line. We aggregate these distances using the variance calculation, squaring the distances to eliminate negative values, and heavily penalize points far from the average. We apply a square root to return to original units, finding the standard deviation. This single number defines your dataset's exact volatility. The final step in this pipeline is visual translation, but you cannot simply pick a chart because it looks appealing. The geometry you choose is strictly dictated by the character we defined in step 1. This bar chart shows that discrete, isolated values require isolated, rigid bars. There is physical space between the data because the numerical values do not blend together. If the data is qualitative, non-numeric categories like car brands, we represent those categories strictly as proportions of a 360-degree circle based on their exact frequencies. And when dealing with continuous data grouped into intervals, we build a histogram. Because the x-axis represents a continuous spectrum, there are no gaps between the blocks. The absolute rule is that the rectangle's total area represents the physical weight of that group. These graphics function as precise geometric encodings of mathematical variance and position. Your ultimate goal is to execute this analytical pipeline on your own, moving from a completely blank page to a proven conclusion. Looking at the assigned course exercises, you see real-world scenarios ranging from studying family sizes to measuring the velocity of cars on a highway. The final capstone exercise challenges you to take a raw list of annual math grades and populate this massive empty grid with calculations. The algorithm is always the same. Define the specific variable, calculate the raw and cumulative frequencies, establish the center of gravity, measure the volatility, and then draw the required geometry. Mastering this pipeline provides the tools to extract clarity from noise, distilling the chaos of the world into a coherent mathematical